Hi, my name is Steve Richmond. I'm the Design Verification Manager for Silicon Labs in Austin, Texas, and I'm here to present our work that we've done this past year with the RISC-V project in open hardware, the verification environment that we've done, and we want to give you an overview of the work we've done and hopefully get you interested enough to take a look at what we've done and maybe even jump in and contribute. So this open hardware has been a consortium of quite a few folks, a couple of which you'll meet later in this presentation, who've come together to really put together a great open source industry standard verification environment. So we'll talk about the verification environment, and then my colleagues will go into a little more detail on some of the work of the reference model, how we do step and compare, and a few conclusions, and tell you what we're planning here in the future. So the verification environment is really meant to be industry standard, using industry standard techniques. Hopefully not something too unfamiliar to any professional verification engineer. Hopefully it has a lot of the look and feel, techniques, and languages that you will see in a corporate IP verification environment that you may be developing for your own environment. Everything's freely available on GitHub. The Open Hardware Group is our GitHub site, and then under Core 5 Verif, you'll get the entire environment and hopefully be able to replicate everything that we've done for this processor. We're verifying a 4-stage embedded processor that adheres strictly to the RISC-V standard ISA for the IMC and the ZI fence extensions. We've done a lot of work to ensure this runs on any system Verilog compatible simulator. We've completed very comprehensive plans, functional coverage, as well as code coverage to ensure the functional requirements for our processor have all been completely met. I'll look into the test bench here just a little bit, give you kind of an overview of it. At the front end of the test bench, we really drive the stimulus by obviously code, since this being a microprocessor. We have multiple ways to drive code to the processor. We can either use the Google RISC-V random instruction generator. We have a lot of extensions on top of that, and we also support directed tests as well. Both of those flows use the same tool chain to compile assembly or C into ELF hex files that can then be loaded into the core and executed. Where we add a lot of value here is the ability to incorporate a reference model, in this case, contributed and supported by our partners at Imperas, that runs in lockstep with the processor, where the scoreboard is comparing all the CSRs, GPRs, and the program flow through the program counter to ensure that on every instruction, what the RTL is executing and writing back to memory and writing back to registers matches what the Imperas model believes also happens. We've also done a lot of work with functional coverage, of course, sampling what instructions we're running to ensure that we're hitting the entire ISA, as well as a lot of assertions and checker models that we've written to verify external functionality, separate, but very important to the ISA compliance in debug and interrupts are a couple of examples of those, as well as quite a few other assertions. So I'll talk a little bit about some of the environment, some of the components that we have if you pick up our test bench and start running it. The components, we have a tracer model. This is effectively the monitor for the processor itself, so reporting what instruction was executed, what program counter that represented, and also internally what registers in the GPR register set, as well as CSRs are being written, so we can track those. My colleague, Greg Tumbush, will talk about the step and compare methodology and how that's managed between the ISS and the RTL tracer. We have a memory model that can stimulate the OBI port, also provides a lot of virtual peripherals for the directed test environment, lots of coverage and assertion properties for the external debug and interrupt interfaces of, everything from the external capabilities of it to how the CSRs react, interrupt arbitration, all those things have a very comprehensive verification plan, as well as properties to ensure that we adhere to all of the functional standards. A lot of UVM agents, of course, OBI again for monitoring powerful functional coverage, debug and interrupt, so we can drive really any kind of random stimulus into the processor there's really no dependence between the checking methodology and the stimulus methodology here, so we can ensure full functionality is tested properly in the processor, as well as a comprehensive coverage model that covers all of the extensions that we're supporting of RISC-V, and also including these asynchronous events occurring in flight with the what instructions are being executed. As I mentioned before, we support both directed and random tests. Of course, you can write as many directed tests as you'd like in assembly or C. We have a BSP package that provides a lot of test utilities for you. And we've done a lot of work with the random test environment, building on top of Google's RISC-V DOE to generate random tests. And of course, we also have a lot of work we've done in the test bench via standard UVM ways to inject irritants into the system, interrupt debug requests, as mentioned before, and of course, stalling interactions on the RAMs to exercise lots of different timing conditions in the pipeline. We have a modern environment that's easy to control, easy to specify tests. We use YAML throughout the environment to specify regressions, test plus args, build plus args, and random control knobs during tests. All of those are well documented in our README files and very straightforward to control what you want your particular random test to do. Core 5 DV is this custom, our nomenclature for the customization layer we build on top of RISC-V DV. We don't want to edit or do anything to RISC-V DV itself, so we use that as kind of our base layer for instruction generation. So we clone that when we're generating a random test. And then our system Verilog layer of Core 5 DV sits on top of that with custom configurations, our custom register fields for in CSRs, most specifically for interrupts. We've made a lot of enhancements to the RISC-V DV, really to achieve all of our coverage goals. We've spent quite a long time as part of this effort to make sure that we achieve all of our functional and code coverage, and a lot of that work is directly related to the Core 5 DV layer that we applied. And so with that, that's the end of my overview of the Core 5 verification environment. I do encourage you to go look at the model, but now to talk more in depth for the reference model that we use, I'll turn it over to my colleague and at Imperas, Lee Moore.
Thanks, Steve. So my name is Lee Moore. I work for Imperas. And at Imperas, we provide processor and platform modeling technologies for architectural exploration, validation, in addition to software design and simulation tools to provide debug analysis and profiling capabilities. So I've been involved with the Open Hardware Group in order to help with the verification. And my primary role has really been the integration of the Imperas RISC-V architectural envelope reference model. The core model itself is encapsulated within a system Verilog module using the DPI to coordinate bus transactions, our fetches, loads, and stores, and also to synchronize our system events such as interrupts and debug requests. Now, the reference model itself is central to the DV plan in ensuring the verification quality of the state comparison results. It provides a full envelope capability of the full set of ratified RISC-V specifications. So this is covering the subset extensions, both ratified and still under development. Additionally, we provide support for differing release levels. For example, in the user specifications, you could mix 2.2, 2.3 with privilege specs of 1.10 or 1.11. And then in terms of subset extensions not yet ratified, the core model also contains many of these which are under development, and examples of those would be the vector and the bit manipulation. Now, this is pretty important because we have many companies who are designing their SoCs, sometimes using these as yet unratified specifications, and they require a kind of pick and mix approach to varying levels of acceptance of these differing subset extensions. The envelope configuration provides this capability across whatever selection is required, so long as they are within a legal set of configurations. And the model itself exists as a binary object, which in this example is linked to the system Verilog executable via the DPI. And in order to control and observe the behavior of the model, it contains both a control and a state interface to synchronize the execution and also to extract out full and comprehensive architectural state for RTL comparison done by this test bench. Now, in addition to the standard set of supported configurations, the Imperas reference model can be extended to support custom instructions and custom state control registers. And more importantly, this is implemented as an extension, not a modification to the existing envelope model. And this ensures that previously verified functionality is not inadvertently modified. It's only extended from whatever the base selected capabilities are. And a good example of this is the inclusion and support of the debug specification, because the debug specification is highly configurable in terms of its potential implementation. And the customized behavior of the debug specification can be described in a side file, which is bound to the base model for this custom integration. Now, as part of the usage of the reference model within the Core 5 verification UVM test bench, the execution is performed in a lockstep or step compare manner. The RTL executes an instruction to retirement and the reference model executes an instruction to retirement. Then the architectural state is compared by extracting data from the two model abstractions. The reference model is able to communicate the differing condition results during instruction execution in terms of, for example, an instruction that proceeds to completion or retirement, instructions which are interrupted by pending asynchronous events such as interrupts or debug requests, and instructions which undergo an exception due to some calculated condition, for example, if you have a misaligned load store. Now, I should add that in the case of the CV32E40P, misaligned load stores are actually handled in hardware rather than trapping to a handler. And of course, this is one of the choice selections which is made as part of the envelope configuration. So how does the execution flow look as part of the overall step and compare process? The state diagram there on the right of this slide shows the typical transitions controlled by the test bench. And the RTL is stepped until either a trap or retirement. The reference model is stepped until either a trap or retirement, and the state transition paths are compared for equivalence. If the two implementations are in agreement, then we loop around, we go again. If there's a disagreement, then we most likely have a test failure, which we need to investigate. Later on, I'll show a little bit more about the tools and the techniques that are used to zero in on the causes of any divergence between the RTL and the reference model. The implemented System Verilog DPI interface provides direct access to a copy of the internal architectural model state, and upon every instruction retirement or execution, this includes the general purpose registers, the control and state registers, and any other mode configurations which are shared. This would additionally support any custom extension resources which are dependent upon the configuration of the core. For example, if the core had support of the F&D extensions, then they would provide floating point registers, both single and double precision. If we had support of the V extension, then this would also provide the vector registers as part of this shared data. And inclusion of the X subset for custom extensions will also provide visibility of custom registers where they were applicable. So finally, the inclusion of the reference model into a third-party environment, as we're talking about here, System Verilog, but equally System C, TLM, or SpecMan, automatically inherits the full capabilities that the modeling technology provides. This means that the usage of the multiprocessor debugger that we have, the tracing tools, the profiling tools, analysis tools are all made available to the user in this same environment. And this can then be further coupled with the RTL tools, such as the waveform viewers, providing a comprehensive view into both the hardware and the software aspects of the design. This can be invaluable when investigating a divergence in the reported state of the RTL and the reference model. And I hope we've got this message across. So thanks for listening so far. Let me hand you over now to Greg Tumbush, who's going to go into a little bit more detail of this from EM Microsystems.
All right, so now I'm going to be talking about the step and compare portion. So Steve talked about the test bench, Lee talked about the reference model, and so the way that we tie those together is through the step and compare. So the Imperas reference model, and I'll use the acronym RM throughout, is used in a step and compare mode. The RTL and the reference model are in sync at instruction level. Okay, so a key here, the reference model is not cycle accurate, and it shouldn't be. It's transaction accurate, or you can also think of instruction accurate. This is invaluable for debug because both the reference model and the RTL are going to be executing the same instruction in the same compare cycle. So if there's divergences, it's relatively easy to debug why. The test bench is what's going to keep the RTL and the reference model in sync. And the tracer, which again Steve talked about, will flag that the test bench that the RTL has completed an instruction and it's time to compare those results against the reference model. So step and compare is implemented as a simple four-state state machine. So the simulation begins with step RTL equals 1, and which causes the RTL to be clocked. Once the RTL retires an instruction indicated by the RTL retire event, which is coming from the tracer, the reference model will be commanded to step until a reference model retire event, in which case then we go to the state compare. Once both the reference model and the RTL have retired instruction, the results can then be collected and compared. Once we leave the compare state, because the comparison is complete, the RTL is clocked again until retirement, and then the cycle repeats. The key takeaway from this reference model, or from this state machine, is that the RTL throttles the reference model. So next I'm going to show a step and compare example. So here we have some example object dump code, and we're going to run this in a step and compare mode. So in this diagram, you can see that the RTL has retired because we have RTL retire event at marked as a 1, and then we have the reference model has retired, which is marked as a 2. And what has retired is the jump instruction. So we're going to do a jump to offset hex 961C. And you can see the state as well. We're going from step RTL to step OVP and back to step RTL. The compare state is in there, but because the compare happens in 0 sim time, you can't see that in a waveform, but we know that it's happening because of the compare event. Okay, so you'll notice that you can see in the waveform a disassembly of the object dump code, but you'll also notice that it doesn't match exactly. So the tracer will disassemble the raw hex code, and it doesn't use pseudo instructions or ABI names. And so the tracer will convert it to a non pseudo instruction or ABI. And you can see more detail in the paper about the exact translation. Okay, so as you can see from the state machine, the compare is done in the compare state. In the compare state, we're going to compare the program counter, all the general purpose registers, and the CSRs. Okay, the PC is very simple, right? It's drill down into the RTL, grab the PC, get the PC from the reference model, and compare. The GPR compare is a little more interesting, which I'll talk about on the next slide. When we were comparing the GPRs, we ran into an issue in which the instructions some of the instructions use the execute write back stage. They will update the GPR, some GPR registers after the RTL retire signal. So in this example, I'm showing a load word to register X8, and it completes at the time shown with the cursor, and because we can see that there is a step RTL, or excuse me, an RTL retire event. But the GPR X8 doesn't update until the time shown on the slide, but the comparison is done before that because the reference model has completed, and then the compare will fail. Okay, so the whole issue here is that the load word loads the X8 register after the retire event because it uses the execute write back stage for that. So the solution here is that the tracer uses a queue called instruction reg write, and that queue is going to contain the address and the data, the address being the address of the GPR, of any GPR updated in the execute write back stage. Okay, so here we're showing the exact same instruction, a load word to X8, but we're also showing now the contents of this queue. So in the first location of the queue, we have an address of 8, which means we're going to register X8, and then the value that's updated in X8 is going to be 364C. So now when the RTL flags retire, we now do have all the information we need to compare that instruction. The reference model will then flag retirement, and then the compare will succeed. Okay, next I'll talk about the CSR compare. So this is pretty simple, because when the RTL retire event is triggered, the RTL CSRs will have already updated, and those can be probed directly. At the reference model retire, the reference model is going to write all the predicted CSRs, in other words, any ones that have changed, to array CSR, which is an array of 32 bits indexed by a string. And the index is the name of the CSR, for example, MISA. So in this, and this is the code used for in the compare function. So the array CSR is going to be fully traversed at every call of the function and compared with the relevant RTL CSR values. So we're going to match, using the index, which again is a string, what register we're comparing. CSR val is going to be loaded with the RTL value, and then a function called check32bit is going to be called, which contains what's being compared, so that you know if there's a miscompare, you know what the name of the register is that miscompared. The expected value is going to be the index into the reference model's array, and then the actual value is what was directly probed into the RTL. Okay, so to wrap up what we've talked about, hopefully we've convinced you that the CV32E40P RISC-V CPU is fully verified. It's open source, both the RTL and the verification. You can download this today and replicate the exact results that I showed and Lee and Steve showed. The functional code and code coverage is at 100%, and all of the tests required to get to this coverage are also at 100%. So we want to take a few minutes and talk about the future work of open hardware, hopefully motivate you to get involved and tell you what's upcoming. So some upcoming work is a CVA6, which is a 6-stage single issue in order CPU, which implements the full 64-bit RISC-V instruction set. This instruction set is rich enough that you can boot Linux on this. The next generation of the processor that we just talked about in this presentation will contain the XPulp extensions, so a lot of performance enhancements. Also in the queue is the CV32E2, which is a 2-stage pipeline instead of the 4 with the CV32E4. And then we're looking at implementing the common tracer interface for the RTL and the reference model, which would greatly simplify the effort required to integrate the core in any step and compare module and in our standard Core 5 Verif test bench. If you're familiar with RVFI, this method will be very similar. And lastly, we're looking at integrating our RISC-V DV generator from Google as a UVM component. Right now, it is written in System Verilog, but it is not usable as a strict UVM component. This would allow us to encapsulate the generator as an extension of a UVM component. So then that environment, the UVM environment, would have direct control of the generator at runtime, allowing much more fine-grained control. And lastly, the Open Hardware Group is a member-driven organization. We are dedicated to the development of open source RISC-V IP. The real work of writing the specs, the RTL design, and the verification is performed by individuals and member companies, all of us coming together for a common purpose. If this is something that interests you or your organization, please contact Open Hardware at openhardwaregroup.org. And with that, I'll open up to questions. Thank you.